In this video, we're going to go into the world of the indefinite integral. We're going to spend a fair amount of time going through different integration strategies, but this is a pretty cool class of problems that you'll see out there, right? So what we've been talking about so far is the definite integral, right? So the definite integral, one of its defining properties is that it has bounds, right? And it outputs a number, right? And we call this net change, also displacement, right? This is analogous to when we look at differential calculus. This is analogous to when we find f prime of c, right? We plug in some number into our derivative and get out a slope. That would be analogous to what we're doing with the definite integral. So as you might expect, there's also a sort of an analogous feature to the derivative that we don't evaluate at any point, right? To the general derivative, and that's what the indefinite integral does, right? So it has no bounds, right? And it outputs a function. And we call this the antiderivative. And this is analogous to, like we talked about, f prime of x, right? So basically the comparison I want you to draw is that what we've been doing so far has been analogous to like finding the exact slope of the tangent line at some point, right? Finding the specific number that is the slope. Of course, in our case, we're finding a displacement or a net change, but now what we're looking at is the indefinite integral, which is analogous to our general derivative, which gives us some kind of a function instead of just a number, right? So that's basically the relationship between the indefinite integral and the definite integral. And this is where we'll be spending a lot of our time moving forward. So calculating indefinite integrals is basically the process of undoing a derivative, right? Because if you think about it, what we've been doing so far is going from velocity to displacement, right? That's what the definite integral has been all about. And that's basically what we're doing here, right? We're just doing it in function form instead of actual numbers. So we're basically just going back in the derivative chain, where displacement to velocity is taking a derivative. Going back from velocity to displacement is what integration is all about. All right, so let's try this thing out here. So we want to find the antiderivative or indefinite integral of this giant function here. So let's look at this piece by piece and see if we can find the antiderivative for each term. Now fundamentally here, let's make sure we understand what we're doing. Basically we are asking ourselves the derivative of what function is equal to 4x. Right? So we're looking at the first term. The derivative of what function will give us 4x? Well, let's think about how we differentiate these things to begin with. So 4x is a polynomial. It's a first order polynomial, but it's a polynomial. And when we work with polynomials, we use the power rule, right? So let's think about how we might use the power rule to get 4x. Well, just thinking about it, the derivative of x squared, if you think about it, is equal to 2x, right? So using the power rule on x squared, or any quadratic, gives us a 2x, or a first order, or a linear function there, right? Which is exactly what we want. So now what we need to do is we need to manipulate x squared just a little bit to make sure that the derivative of whatever we have here becomes 4x instead of 2x. So all we need to do is multiply everything by 2. So if we multiply everything here by 2, what we end up with is that the derivative of 2x squared is equal to 4x. And that's exactly right. Yeah? Derivative of 2x squared is equal to 4x. You can verify this for yourself using power rule. But this right here, what we've calculated over here, is our first antiderivative, right? It's some function such that when I take its derivative, it gives me this 4x, this original thing that I'm looking for, right? So that's basically the whole thing we're trying to find here. And so the first term here, which is our antiderivative of 4x, is going to be 2x squared. Right? Awesome. Now, the next thing we want to look at is this x cubed here. Now, I encourage you to see if you can think about this the same way using the power rule and figure out what this antiderivative might be. Take a second, pause the video, see if you can figure that out. So I hope you had a chance to think about that, because we will go ahead and work through that right now. So once again, we're fundamentally asking the question, derivative of what function equals x cubed? Well, remember the derivative of x to the fourth, right, equals 4x cubed. And that x cubed there is exactly what we want. Except instead of 4x cubed, we just want 1x cubed. So we're going to divide everything. We're going to divide everything by 4, or multiply by 1/4. Okay? And so what this gives us is that the derivative of x to the fourth over 4 is equal to x cubed. And once again, this guy right here, what's next to the derivative symbol, this guy right here is what we are trying to find. Right? This is our antiderivative or indefinite integral. So we're just going to tag on x to the fourth over 4. And that's the antiderivative of x cubed. Okay, great. Next one is secant squared of x. This one's a little trickier because we can't quite use the same power rule thing we've been thinking about. But we can just remember that if we think back to our trig identities, we remember that the derivative of secant squared of x, or excuse me, derivative of tangent of x is secant squared of x. Right? And so therefore, that right there is our antiderivative. Tangent of x is the antiderivative of secant squared of x, so we can just tag that guy in there right now. Okay? And then last but not least, we can look at e to the x. And e to the x is really, really nice because remember, we don't need that, remember that the derivative of e to the x is still e to the x. E to the x is its own derivative, and so therefore e to the x is also its own antiderivative. Right? And that right there is our first antiderivative. Right? Now let's see if we can check this answer by taking a derivative. Yeah, we can check this answer by taking a derivative. Right? So if I took a derivative of this, derivative of, right? Well, what would this come out to? Well, derivative of 2x squared using power rule, that's just going to be 4x. X to the fourth over 4, derivative of that, multiply by 4, they'll cancel, so we'll have just x cubed there. Derivative of tangent of x, again using our identity, secant squared of x. E to the x, derivative of e to the x, of course, is just e to the x. Right? And as you can see, this derivative that when we take the derivative of our antiderivative, we get back the same thing over here, right? So that tells us that our solution is correct. We've done our job correctly. And this is something you should do whenever you're doing any kind of basic antidifferentiation, right? Always take a derivative and check your answer. It's a really quick way to just make sure you're doing these things right. You can save yourself a lot of time, effort, and even test marks if you're doing this on a test. One last thing I want to draw your attention to. Excuse me. What would happen if I say, let's add plus 7 to this equation? What would this derivative be now? It would be exactly the same thing, right? Because derivative of 7 is 0. What if I added pi here? Would that change what this derivative would be? It would not, right? I could put any constant I like here. I could put pi, I could put 6, I could put 9, I could put 7, I could put e if I wanted to. No matter what constant I put here, its derivative is always going to be equal to this thing over here. And that's why we need to have one more little component in here, and that is a plus c in our antiderivative, right? Because that plus c tells us, right, that we could have any constant here and this equation will still satisfy this antiderivative thing here, right? If I take this derivative, it will still give me this original thing. That criteria will still be satisfied no matter what constant I have here. So therefore, we need to always have this plus c over here, right? It's very common for people to forget that. Just make sure you don't. So always have a plus c over here at the end to make sure that we are taking into account that we could have any finite constant here that we wanted, and it would still give us that same derivative there. Okay, awesome. All right, so I just wanted to wrap up this video with a couple of common antiderivatives that you should know. So for example, in the last parts of the problem we just did, we took advantage of these two specific identities here, right? The antiderivative of e to the x is e to the x plus c, antiderivative of secant squared of x is tangent of x plus c. Just like that, there's a whole bunch of other very helpful ones that it's good to know. But also just bear in mind, this is not going to be too much more work in the way of memorization, because all of these are heavily based on our differentiation rules. So if you remember that the derivative of ln of x is 1 over x, for example, it's not too hard to remember that the antiderivative of 1 over x is ln of x. However, just a few words of caution. Be careful about the signs of certain things or the positioning of certain terms. So for example, in sine of x, the derivative of sine of x is just cosine of x, but the antiderivative of sine of x is actually negative cosine of x, right? Because remember, the derivative of negative cosine of x is the derivative of sine of x, the derivative of cosine of x is negative sine of x. So be very careful about that. And also the positioning. So for example, the derivative of a to the x is a to the x ln of a, but when we're finding the antiderivative, it's a to the x divided by ln of a. So be very careful with that. And then lastly, the antiderivative of x to the a. So we talked a little bit about this and what we were doing. We'll come up with a more general formula for this in the next video. So with that, thank you for watching, and I hope to see you in the next video. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!